Welcome back. So today I'm going to tell you about Stokes' theorem and Green's theorem, which are vector calculus formulas, a lot like Gauss's divergence theorem. So they allow us to relate surface integrals of the curl of a vector field over some surface to the some equivalent contour integral around an enclosing contour. Okay, these are really useful theorems, Stokes' theorem and Green's theorem. And just like Gauss's theorem can be used to express kind of physical quantities in partial differential equations, we can also use Stokes' theorem in a very similar way. So Gauss's theorem has to do with like volume integrals of the divergence of a vector field. Stokes' theorem is going to have to do with surface integrals of the curl of a vector field. So I'm going to jump in. Okay, and essentially we are looking at a surface, kind of an open surface in 3 dimensions. So the surface is given by S. And we're going to assume that the surface has kind of an edge or a perimeter that we're going to call partial S. Now this is just notation. This doesn't mean we're taking the derivative of S. This is just sometimes in kind of manifold theory, if you have a manifold or a surface, the boundary of that surface is 1 dimension lower. So if this is a 2-dimensional surface, this is a 1-dimensional curve. And sometimes we just denote it by partial S. So this is purely notation. And we're going to assume that you can have a tangent vector along this pink curve. So at every point, there is a little tangent vector that we're going to call ds arrow. It's literally a vector with an x and a y component. Okay? Similarly, at every patch on the surface S, every little kind of patch of S, there is going to be a vector in the normal direction with area given by dA. And so we're going to call this vector dA vector. Okay? Important. It has the magnitude of the area of that patch, and it is pointing in the normal direction. This is important. Good. Now, I'm going to write down Stokes' theorem in full generality, and then very quickly I'm going to go to Green's theorem because it's much easier to understand kind of how things works. Green's theorem is like a 2D flat version where instead of a surface, we're just, it's kind of a flat surface, and we are working on its perimeter. Okay, good. So Stokes' theorem here is, I'm going to write it as the integral around this entire surface. So the surface integral of the curl of some vector field. And of course, I should always mention, there is some ambient vector field kind of going through my volume. We're going to call this big F. And it's going to have components F1, F2, F3, just like it always does. And it's kind of passing through this volume. And if you like, you could also think of maybe there's just a vector field on the surface of this volume. Maybe this is the northern hemisphere, and I have some vector field, which is the, atmospheric flow dynamics, hurricanes and things on that northern hemisphere. Or you can think of an oil, like a little bubble, a soap bubble. You can see the film, the vector field on the film. So there's some vector field F that is defined on the surface. It could be a 3-dimensional vector field, and we just are looking at how it affects the surface, or it could be a vector field on the surface itself. And so we're going to take the surface integral of the curl of our vector field. And remember, the curl of a vector field itself is a vector field. So this is also a vector quantity. So essentially what I'm going to do is I'm going to take my vector field and I'm going to compute the curl at every little patch here. Every little patch I'm going to compute the curl of my vector field. And I'm going to integrate those up all along the whole surface. And what I'm going to do is that curl should be pointing, I want to see what is pointing normal to the surface. So I'm going to dot that with my dA vector. So this is kind of like integrating around the whole surface times d area. But because this is a vector field itself, I'm dotting it into the normal direction. Okay, and I'll kind of give you some intuition for why we're doing this. This has a direction a little bit later. But anyway, we're trying to keep track of all of the curl. If we add up all of the curl of the vector field on this surface, what does that equal? Sometimes I would care, like maybe the integral of the curl on that surface tells me how strong the hurricane is going to be. And that surface integral, just like Gauss's theorem allows us to take and equate volume integrals and surface integrals, Stokes' theorem allows us to equate this surface integral to a path or a contour integral along this pink curve. And so the integral of my curl over the surface is equal to the integral around the perimeter on this pink curve of my vector field f dotted into this little tangential ds direction, this little ds. And so this is actually a really, really nice expression. This is a very easy to compute quantity. I literally just walk around this perimeter and I take my f vector, maybe my vector field is pointing, I don't know, maybe my flow is pointing in that direction, that's f. And I just dot f with ds, and I keep track of how much of the f vector field is kind of in this tangent direction. And if I add that up around this whole curve, it basically says how much of f is kind of swirling around. If I am keeping track of the amount of f that's tangent, how much of that f is kind of in this tangential direction. And that's a measure of the curl or the circulation kind of the vector field on that perimeter. That's what this is. And that's really remarkable that if I just keep track of how much my vector field is in this tangential direction, kind of over this closed orbit, again, that tells me how much kind of like circulation or flow around this, this perimeter I have. That is equal to if I computed the curl at every patch on this surface and added all of those contributions up. So that's what Stokes' theorem is saying, and it's a pretty remarkable theorem. Okay, so I want to show you how this works in Green's theorem because I think it's really a lot easier to restrict this surface to be flat and look at Green's theorem. So that's exactly what Green's theorem is. So Green's theorem is essentially Stokes on a flat surface S. Okay, so what we're going to do is we're going to look at kind of a top-down version of this, where now we have our surface S. We still have our perimeter partial S. And essentially what we're going to do is write this expression here, but looking at this 2D flat surface. So now my surface is flat, and we're going to do the exact same thing. And I'm still orienting this curve so that it moves in the, I believe, counterclockwise orientation. Okay, that conforms to the right-hand rule, so we consider this kind of the positive direction along that perimeter. Okay, good. Now, Green's theorem is exactly Stokes' theorem restricted to a flat surface, and we can write it down pretty simply. So I'm going to write this down, and we're going to say now that our f here, f in 2D, just has two components, f1 and f2. And any curl that I have, if my vector field is doing some, maybe it's doing some swirly things like this, I have some kind of like circulation components, doing some circulation, then the curl is going to be pointing out of the board. So any positive curl is going to be in the kind of k or z out of the board direction. Okay, so that's why it also helps to think about this in 2D, because all of the curl is in the kind of out of plane third component. And so Green's theorem, or Stokes' theorem on this 2D slice, essentially simplifies to this surface integral. So this integral over S of the curl of my vector field. Now the curl of a 2D vector field is just partial f2 partial x minus partial f1 partial y. And now if I think about it, every little area patch, the normal is already in the z direction. So I just have to multiply this by the little d area patch here, which is dx times dy. Okay, so this is a simpler expression for this integral of the curl here. I'm just integrating up the curl of this 2D vector field over this entire surface. And Green's theorem says that this is equal to, again, it's equal to my vector field f dotted into the tangential direction, into this little tangent direction. So if I take, if I have this little ds vector, and I have my f vector, I just go along the perimeter adding up what is f dotted with ds, okay? And so the nice thing is that this is an integral around the perimeter of f dotted into the tangential direction. But because I'm already moving around this curve that's parameterizing the perimeter, this is essentially just f1 dx plus f2 dy. Okay, so I literally take how much of f1 of the f1 component is in the dx direction of this little. Sorry, I'm getting ahead of myself. Let me slow down. This little ds vector is equal to dx dy. It tells me at every little point here, is my vector moving more in the dx direction or the dy direction? It tells me what the direction of my curve is, dx, dy. Those are the dx and dy here, okay? And we integrate all of those little dx's and dy's along this surface. So this is Green's theorem. And again, it tells us that I can basically just walk along the perimeter of this vector field, adding up this quantity, just literally taking f1 dotted into the dx component of this tangent vector, plus f2 dotted into the dy component of this tangent vector. And if I add up that number around this entire perimeter, it equals the sum of all of the curl of my vector field on the entire surface integral. So again, this is a lot like Gauss's divergence theorem, where we're going from a big integral, over a volume down to a smaller integral over a surface area. Here, we're going from a big integral on a surface down to a smaller integral on the perimeter of that surface. And the same thing here. So here's a couple things I want to do. I want to give you some physical intuition for why Stokes' theorem and Green's theorem are true. And then I'll tell you some cool examples of these. Okay? So maybe the first thing I'll do is I'll just draw this picture again. And we're going to do the same kind of pillbox decomposition that we did before for Gauss's theorem. So what we're going to do is break this up into a number of little boxes. So I have my kind of kidney bean shape here for the surface. And we're going to break it up into a bunch of little boxes. Now I've only drawn 12 boxes here, but what we're going to do is essentially imagine we take the limit as these boxes get infinitesimally small and infinitesimally close together. So this is going to be a really, really finely resolved graph paper kind of representing this area. And so what we can do is essentially look at the curl in every little box here. So the little local curl in every little box is kind of a little vector field that's going around in a circle. This is a little positive curl representation here. And the next thing is going to have a little curl. These are all going to have, a little bit of curl. And I'm just going to draw these. And just like Gauss's divergence theorem, you can already start to see what's about to happen is that the inner cells, the curl from the neighbors are going to cancel each other out. And so if I integrate all of these curls over the entire area, all of the inner kind of components of the curl are going to cancel out to 0, and I'm only going to be left with the component that's kind of in this tangent direction around the perimeter. And so that's the real idea here. Maybe I don't have to draw the whole thing, but I think you get the idea, hopefully, that just like Gauss's divergence theorem, if we have these infinitesimal little boxes, and if we assume that our vector field is sufficiently smooth that these are continuously varying from cell to cell, so if F is a smooth vector field, and most of the vector fields I think about are smooth. Fluid flows are smooth typically, except for shock waves. The flow over a soap film is smooth and continuous. And so that basically means that these different kind of components on these different edges are canceling each other out. This little box is swirling a tiny little vortex. This little box is swirling a tiny little vortex. And the up component and down component cancel each other out on every single inner wall here. And so all that's left are the little components that are kind of in this tangent direction here. that are kind of aligned with the tangent of the perimeter. And so hopefully that gives you at least some intuition for why the surface area of the curl is equal to a path integral of the vector field dotted into the tangential direction. The tangent component, the component of the vector field that is tangent to this enclosing pink perimeter. Okay, so that is at least the cartoon of why Green's theorem is true. And Stokes' theorem is just kind of a more general case of Green's theorem, where you now take this, this two-dimensional surface, and you imagine that there is some three-dimensional surface over this perimeter. And the same basic argument applies. If I grid this up into little boxes, and I look at all of the little curl components, all of the inner kind of inner walls are going to cancel out. And the only component that's going to be left when I integrate over this entire blue surface area is the part of the vector field that is tangent to this pink perimeter curve. So again, the integral of the curl of f over this entire surface is going to equal the integral over the little contour, the perimeter of my vector field dotted into the tangent direction, just the tangential component. And this is really cool. If we think about, let's say we're talking about planet Earth, and so we have, we're going to look at the northern hemisphere here. And let's say I have a big, I'm not sure I can draw a big hurricane, but let's say I have, some big hurricane forming in the northern hemisphere. If I added up all of the curl of every little patch on this northern hemisphere, that would equal to the amount of the vector field integrated along this perimeter dotted into the tangent direction. And so you can think about it, if this vector field is swirling around in this surface, there will be a signature of that swirling on this pink perimeter here, and we'll be able to compute kind of how much circulation or vorticity there is in this surface just by computing what is the accumulated amount of circulation on this, this perimeter here. So it's a really powerful idea. And this is going to be useful for things like fluid flows where we have circulation and rotation. So this is actually really useful when we think about airfoil theory. So if I have a wing, I might want to compute kind of how much, what is the circulation of flow kind of over that wing. And that will be relevant for computing the lift over the wing, things like that. So curl and Stokes' theorem are really important when we think about aerodynamic surfaces and fluid flows over aerodynamic surfaces, hurricanes, things like that. And this is going to be how, remember, divergence theorem is how we encoded conservation of mass, conservation of momentum into Navier-Stokes equations. Stokes' theorem is how we're going to encode conservation of angular momentum. So all of this curl is kind of measuring how much angular momentum I have. And if I add up all of that angular momentum, there's a signature of it in the perimeter of that surface. So really, really powerful idea here. And one last thing I'll point out, and this is just something neat. I remember one of my favorite calculus teachers in high school taught us this, and I think it's a really cool idea. You can also use Green's theorem or Stokes' theorem to compute the area of a tract of land. So back before GPS, back before you could just kind of use satellites and GPS to compute the area of an irregular shape of land or use a computer program, surveyors would actually have to walk around the boundaries of someone's property. So maybe I have a farm here, and I have another farm here, and I have another piece of land here, and maybe there's a river, that's going, on the boundary of these. How do I compute the area, how many acres or how many hectares of land are inside this area if I want to sell a parcel of land and it's got an irregular boundary? Well, it turns out you can use Stokes' theorem for this in a really clever way. So let's say I pick, one of these areas here, S, one of these irregular shapes, S. Then the area of S is equal to 1/2 times the integral around its perimeter, around the perimeter of S, of x dy minus y dx. And I'll tell you why this is true. So this is true And so what I can literally do is I can walk around. I can go, I bring an apple and a nice book, and I'm walking around this perimeter, and I literally count how many times I step in the dy direction versus how many times I step in the dx direction as I go along this perimeter, and I add them up in this formula. So I literally, as I walk around this perimeter, I compute this quantity. And when I come back to my starting point, I will have swept out the area of S. Now, why is this true? This is true specifically because our vector field here, this corresponds to a vector f that equals minus yx. And so if I think about it, the curl of this vector field, so the curl of f, is equal to partial of f2 with respect to x, that's 1, minus partial of f1 with respect to y, that's minus 1. So this curl equals 2. So if I do a surface integral over S of the curl of my vector field, dA, that should equal 2 times my area, 2 times this area. Let's call it A, okay? But I don't want to actually break this up into a bunch of little surface areas. I don't want to actually parcel this out to measure the area. So we're going to use Stokes' theorem, or equivalently Green's theorem, because this is a flat surface, to instead integrate around the perimeter. So this is equivalent to the same integral around the perimeter of my vector field, f, dotted in the perimeter tangent direction. And again, f dotted into the perimeter tangent is minus y in the dx direction plus x in the dy direction. That's what this quantity is. And so if I just integrate this quantity around the perimeter, it's the same as 2 times the area of the parcel. So that's why I divide by 2 here. So long story short, if you want to measure the area of an irregular shape, you can just walk around the perimeter and compute this quantity along the perimeter of the surface, and you can then get the area. So one of my favorite examples of this is you can compute the area of pretty interesting shapes like these hypocycloids just by kind of parametrizing this and walking around the perimeter computing this quantity. Okay, so that's Stokes' theorem and Green's theorem. It essentially allows us to quantify conservation of angular momentum or curl or vorticity in these kind of rotational flows in a similar way to Gauss's theorem for quantifying conservation of mass using divergence. It turns out mathematically there is kind of a higher dimensional, an n-dimensional generalization of Stokes' theorem and Gauss's theorem, and you can almost kind of unify those. It's a little bit outside of, it's a little bit more sophisticated than what I can show you with kind of simple vector calculus. It's more doing calculus on n-dimensional manifolds, but it's really, really interesting, interesting kind of concept that you can actually generalize this to n-dimensional surfaces. Okay, good. So Stokes' theorem, Green's theorem. In the next few lectures, we will likely be talking about things like potential flow and which vector fields have rotation, which vector fields are irrotational, and things like that. All right, thank you.